Okay, so now we're going to get into another way of expressing the concentration of a solution, and that is known as molarity. And by definition, molarity of a solution is basically the number of moles of a solute in a liter of the solution. So that's molarity. All right. Mathematically speaking, you can express it this way: the number of moles of the solute divided by liters of solution. All right. Now, the units of molarity is moles per liter. That's one way of expressing the units. Another way is simply by using uppercase M as the units, right? So, um, as I said before, that's a unit of moles per liter for molarity. Um, and therefore, you can rearrange this equation. Well, actually, this here is giving you something that you should know already, the moles of solute. That's the grams of solute divided by the molar mass. So another way of expressing molarity is plugging this here, this part of this expression where you have moles of solute, and when you do that you end up with this expression right here. All right. Um, so we can rearrange this to express it this way. It's saying the same thing, just different ways of expressing the same idea. All right. So to prepare a solution of a particular concentration, you have to be careful. You have to take certain steps in order to get as accurate an expression of the concentration of the solution that you're trying to make. So what we're looking at here is how we make up a 1 molar solution, or a solution that is 1 mole per liter. So what we do, of course, we have to know the amount of solute that we need. So that will take some calculations. You'd have to actually sit down and calculate the amount that is equal to 1 mole. Of course, you're going to need to know what the molar masses of the different substances are, or different elements are in that compound, to determine the mole. So once you determine that, then you put that in this piece of glassware, which is known as a volumetric flask. A volumetric flask is basically specially designed so as to accurately measure one set volume of a mixture or a solution or a liquid that's in it. So they come in different sizes. So what you see here is a 1 liter flask. There's a mark that is etched on the stem, which represents the 1 liter level, and it is very accurately made. In fact, if I'm not mistaken, it is accurate to 2 decimal places when expressed in liters, or actually when expressed in milliliters. All right, so it's a very accurately made piece of glassware, and that's why when you're handling it, one of the things that you should not do with it is heat it. So you should not put it in an oven, for example, to dry it, because of course, as we all know, most substances when heated will expand. Glass is no exception, and therefore if you put this piece of glassware in an oven, it will expand. If you take it out, it will contract, but there's no guarantee that will contract to its original volume, and therefore you have basically ruined a very expensive piece of glassware. It won't be able to measure accurately the volume of 1 liter of any liquid that you place in it, because it is now expanded and contracted, and that ruins its function. So if you're working with any glassware of this type, please be careful when handling it. Do not subject it to extremes in temperature, because that will basically destroy its function. In any case, so what we do here is, as I said before, you put your solute in the flask, and then what you do is add water, but you don't add water all the way up to the mark immediately. You add water to the level shown here. You stopper it, you shake it up to make sure that the solute dissolves. Once the solute has dissolved, then you continue to add water carefully, preferably dropwise, until the meniscus gets to the 1 liter mark. And therefore, you would have successfully made the solution of the desired concentration, in this case, 1 molar. Okay, so how do we use the equation to calculate the molarity of a solution? So here is an example. The question talks about acetic acid. The number of moles is 1.4 moles. The volume is 250 mils. So basically, what you have to do first is convert the volume to liters, because remember, molarity is moles per liter. So we divide the moles by the volume, but of course the volume has to be converted to liters, and then whatever you get will be the answer, which is 5.6 moles per liter, or as I said before, mole per liter can also be expressed as uppercase M, so 5.6 M would be the molarity, and that's how you do this particular problem. All right. Okay, let's look at this example. Now in this case, they gave you the molarity, they gave you the volume, but they're asking for the grams of potassium hydroxide. So what you'd have to do is start with the volume, convert it to liters, and then convert the liters to moles, and then from moles to grams. So you're given the volume in milliliters. You have to, you're given the molarity, and the molar mass, of course, you can determine that from the periodic table. So to do the calculation, we start off with the volume. As we said before, we have to convert from the volume in milliliters to liters. So we multiply by the appropriate conversion factor. And then we multiply by the molarity to convert from liters to moles. So that's why we use this conversion factor. And then finally, we convert from moles to grams by using the molar mass. And of course, we're going to have the final answer being expressed in grams, because we have the appropriate units being cancelled out. The only unit remaining after all the other units are cancelled out would be the gram unit. Okay, so that's how that is done. Okay, here's another example. In this case, they gave you the molarity and they gave you the volume. You're asked for the number of moles. So basically, you have to rearrange the molarity equation to get an expression for moles. Basically, the moles will be equal to liters times molarity. But because we're given the volume in milliliters, we have to convert from milliliters to liters. So that's what we do first. And then we multiply that value by liters by the molarity, which is 16 molar. So we plug it into the equation. And the final answer, according to my calculations, would be 5.2 moles of nitric acid. Okay. So that's basically how that is done. Here's another example. So as you can see, problems involving molarity can come in different ways. In this case, you're asked for the volume. They gave you the mass of the solute, potassium carbonate, and they gave you the molarity. So what you'd have to do firstly is convert from the grams to moles. We can easily do that. And then convert from moles to liters. We can do that because we have the molarity. So this is the data that is given in the question. And this is basically how we set it up. We start off with the mass in grams, convert that to moles by dividing by the molar mass, and then we multiply by, or divide I should say, by the molarity, and that's it. The only unit remaining after cancelling out all the other units would be the liter unit. Okay, here's yet another example. In this case, they gave you the mils of hydrochloric acid. They gave you the mass of sodium hydroxide. Now this one is a bit different because in this case it's a stoichiometric type problem where you have to first write down a balanced equation for the reaction, right? So that's the first step. We write down the balanced equation for the reaction. If the equation is not balanced, more than likely the subsequent calculations would be erroneous. Next step is that we determine the moles of sodium chloride, or I should say sodium hydroxide. Now they gave you the mass, which is 28.0 grams, so we'd have to do the conversion. Of course, we need to determine the molar mass of sodium hydroxide, which is 40.0 grams, so we do that conversion and we end up with the moles of sodium hydroxide. Now that we have the moles of sodium hydroxide, we look at the balanced equation, we see there's a 1-to-1 mole ratio between those two, right? So therefore, let me just go to the next slide. So therefore, we multiply by the conversion factor, which allows you to convert from moles of sodium hydroxide to moles of hydrochloric acid, right? So that will give you the moles of hydrochloric acid. Then, using the molarity, we can determine the liters of hydrochloric acid. So this would be the conversion factor that represents 2 molar hydrochloric acid. And then, since the question is asking for how many mils, we convert the liters of hydrochloric acid, which is 0.350 liters, to milliliters. So the next step would be we multiply by this conversion factor, which allows us to convert from liters to mil, and therefore your final answer is going to be equal to 350 milliliters of hydrochloric acid. Okay, so this is a summary of the different types of concentration expressions and units. Now we have done mass percent and mass per volume percent and molarity. Those are the ones that we have done so far. We have not done parts per million. We have not done volume percent. Oh yes, we have actually. We have done volume percent, and we have not done molality. In fact, we won't be doing molality at all in this course. But for those of you who plan to do general chemistry, especially general chemistry 2, you will certainly meet this unit and way of expressing the concentration of a solution. Okay, so let's talk about dilution problems. Very often in chemistry, in any chemistry lab, doesn't matter if it's a high school lab or a college lab or even a major research facility, chemists are very often faced with a problem of needing a solution of a particular concentration, but at hand they would have a solution of the same substance at a greater concentration. So therefore, what is needed is a more dilute solution, and therefore the chemist will have the problem of making sure that the more concentrated solution is diluted to the correct extent to get the required concentration. All right? So what happens when a solution is diluted? Well, basically what you're doing is adding more solvent, and thereby what you're doing is increasing the volume of the solution. But the amount of solute that is present remains the same. So here we have a situation where the volume increases, but the number of moles of the solute is constant. So what that results in is a solution of a lower concentration. So if you take a solution like sodium nitrate, right, which is what this diagram represents, and then you add more water such that the solution volume is doubled, then basically what you're going to have is a situation where the concentration of the solution will be halved. All right? So that's what happens when you dilute any solution. You're increasing the volume, but the number of moles remain the same. So therefore, the solution will have a lower concentration as a result. All right? So here is an example of a dilution problem. So the question says, calculate the molarity of a sodium hydroxide solution that is prepared by mixing 100 mils of 0.20 m sodium hydroxide with 150 mils of water, right? So what we have to do is first identify what the initial volume and the initial concentrations are. So the initial volume is V1, 100 mils. The initial molarity is M1, 0.20 m. Now, the question says that 150 mils of water was added to the 100 mils of water, right? Now, since the question says that we are to assume that the volumes are additive, then we can conclude that the final volume will be 100 mils plus 150, which is equal to 250 mils, right? And the question is asking now for the new molarity. Now, basically, the relationship between M1, V1, V2, and M2 can be given by this expression right here. M1, V1 is equal to M2, V2, all right? So therefore, if you want to find M2, basically, what you could do is plug the numbers in, right? And then you basically divide both sides by 250, and you're going to end up with M2 being equal to 0.80 m. So that's basically how we calculate the new molarity if you're given the other information, the initial volume, the initial molarity, and the final volume. All right? Okay, so that's basically how you do this. Now, let me just say something about the use of this equation. It doesn't matter what the units of volume are. It could be milliliters, it could be liters, it could be gallons, it doesn't matter. And it doesn't matter too what the volume of, or I should say what the units of molarity are in this case, right? As long as the units are the same on both sides for both volume and concentration, right? So for example, if you were given the concentration here in grams per mils or in percentages or whatever, in other words, if it's not molarity but some other way of expressing concentration, then as long as the units are the same here and here, then the equation is, you can plug the numbers into the equation and solve it easily. All right? Okay. Here is another example. Now, this one is another stoichiometric type problem because in this case, it's a reaction between two substances, silver chloride and barium chloride. No, I'm sorry. Let me see. Actually, between silver nitrate and barium chloride to give you silver chloride. So again, the first and foremost thing you need to do is write a balanced equation for this reaction. So that's the equation right there. And then we determine, firstly, based on the volume and the molarity of barium chloride, we can determine the moles of barium chloride. So of course, what we have to do is convert the volume to liters because you gave you the volume in milliliters. And then you have to multiply that by the molarity according to this equation, and that gives you the moles of barium chloride. Now, based on the balanced equation, the mole ratio between barium chloride and silver chloride is a 2-to-1 ratio. So therefore, what that means is that we have to take the moles of barium chloride, the 0.60 moles of barium chloride, and we have to multiply it by basically 2 to convert from moles of silver chloride to moles of barium chloride. So this is the conversion factor that is used. And then, because the question is asking for the grams of silver chloride, we have to convert from moles of silver chloride to grams by multiplying by the molar mass of silver chloride. And then do your computation, and that's basically how you get your answer. Now, there's one error here. This should not be crossed out, because you're going to end up with grams of silver chloride here. But apart from that, everything else is correct. Okay, so that's basically it for this chapter. Until next time.